And this is, yeah, so this is just recording for folks who want to look at it. So, all right. So I think the plan for this meeting was we had talked in February about, what are the things that we really need from this community. And one of the things that we had talked about a lot was that people really want to have a sense that, what they're doing is productive, and to have some way of developing some confidence that their students are learning beyond sort of their own, their own personal assessment of it, right? And so the discussion we had was, well, if we want to think about assessment projects, then we have to think about developing some community goals around this. And so one of the things I sent out to y'all is that link that's there. We're actually doing this at my institution we have a committee that's devoted to developing computational learning goals for our department. And it has sort of I would say a slightly different flavor than I'm used to doing from a curriculum development standpoint. But that's, I think, because a lot of different faculty are involved. But the things that I'll draw your attention to are on page, in that PDF, I think it's like page 9. So yeah, page 9. So we're focused right now on our majors. So we're focused on sort of the core courses for our majors. And the first draft of our learning goals is focused on E&M 1, which is the Griffiths course, essentially. It's the statics course. And so if you look at page 9 and you kind of scroll down, to the after completing electromagnetism 1, PHY 481, students should be able to, there's a list of a bunch of things. And those are not like full consensus goals. We haven't discussed those, right? Those are drafts that people are iterating on. But they're the ones that are definitely the most complete. And if you keep going, you'll see just kind of like topical lists and stuff, which are not really goals. So the idea is that, I'd like to sort of have a discussion with everyone about, what are the goals that they have for computation in general? And then are there things that people think are important for specific courses? And then we can just kind of start there. Since I'm already working on this from my institutional standpoint, sort of like bringing this information in and bringing our information back and sort of, acting as a mediator, I'm happy to do. Or go between, whatever.
So I think this is great. When I look at the list, I see things that we do in my computational physics class. But yeah, so I like the things that you guys have listed here.
Sorry, I was muted. Okay, are there so maybe the thing to start with, instead of, because I know people probably have different interests in different topics, are there things that you want students to get out of just doing computation in general? And are those things different, maybe if you're thinking about sort of your introductory courses where you have students that might not be majoring in physics versus students who are, going to potentially earn a degree in physics? What do those things look like? And I'll just take maybe some notes while people are talking and thinking out loud.
Yeah, I can mention one thing. So I think it was in this document that you've been on an earlier page talking about the difference between pencil and paper algorithms, focusing on continuous algorithms, and that's sort of the calculus or algebra, that we're used to being, especially in really in all classes, but especially in introductory physics. And so that's one of my major goals, is to at an introductory level for sure. And also, I've kind of done this in a upper level mechanics class to try and encourage the discrete algorithms, both as a different way of thinking about the physics and also just like a different solution method that is sometimes more powerful or can apply to different problems.
Can I ask you to unpack that a little more, Sean? So when you say thinking about the discrete problem, what are the kinds of things that you want students to think about when they're thinking about the discrete problem?
So I guess, I mean, like just taking kinematics as an example, you know, I think students think of that, you know, as just some magical formula, right? And you're trying to figure out which parts you know and how you can kind of combine the different equations to get to the end. And sort of, I mean, it's a method for relating the beginning point to the end point, right? Whether that's in terms of distance or in terms of time. But thinking about, I think the discrete, computational method focuses on the sort of instantaneous effect of what a force or an acceleration, if you're just thinking, starting with kinematics, how that changes the other quantities. So as a step-by-step process, instantaneous at each time step.
Right. So it's more representative of thinking about like the dynamics, right? Like what the dynamical relationship is between the forces and the motion.
Right. And I mean, it's kind of, the mistake that when you're teaching students both, like the mistake that I think kind of exemplifies that difficulty is when students always want to put in time instead of change in time when they're doing their computational, if you're doing like an Euler method. Mm-hmm. So thinking of why you use total time for the kinematics, but dt in the computational.
Right. So why t in the continuous? Cool. Yeah. So someone joined us. Stephen, can you hear us?
Yes, I can.
Okay. Have you joined us before? Would you be willing to introduce yourself to us?
No and yes.
Okay, great. And we'll do the same. So we've all been on these calls before, so we didn't start with any introductions.
I'm Steve Gottlieb. I'm at Indiana University. I've been teaching computational physics since the late 1980s, mostly to seniors and graduate students. This past fall, I taught what was supposed to be a sophomore level course based on Python. Is that sufficient?
Yeah, great. Thank you. Maybe we'll go around, just introduce ourselves to Steve real quick. So Michelle, we'll start with you because you're in the upper left corner on my screen.
But she's muted.
Oh, you're muted.
Hi, I'm Michelle Kucher. I'm a professor at Davidson College in North Carolina. I'm a computational scientist by trade, but I'm now a physics professor, and I also teach computational physics.
All right. Sean, you want to go next?
Sure. I'm not on mute, right? Okay. So I'm Sean Bartz. I'm a visiting professor at Macalester College in St. Paul. And I teach introductory physics and various other upper level classes, but we don't have a course specifically in computational physics at this time. And so I've just been, using this group to get ideas of how better to implement computation in introductory and upper level undergraduate courses.
Yeah, I guess I'm next.
Yep.
I'm Tony Musumba, and I teach physics at Bismarck State College. It's a 2-year college in North Dakota. And I do teach computational physics, not as a separate course, but I have it integrated in my introductory physics 1 and physics 2 classes. So using Python, VPython. Is that enough?
Yeah, that's great. Thanks. So I'm Danny Caballero. I'm a faculty member at Michigan State University. I'm also a member of the PICUP leadership, and I I'm actually a physics education researcher, nonlinear dynamicist by training originally, but now I do computational physics education research. And so I try to understand how students learn what they learn from doing computing in physics. And I also teach, right now I'm teaching upper level electrodynamics, where I'm doing a little bit of computing in it right now. That's me. Cool. So just to catch up, Steve, what we're talking about. So I sent out a document which you may or may not have seen. So let me, well, it's actually, so in the chat window here, which I'll paste it in again, there's a document that we are taking some notes in. I just try to keep track of the things that we talk about. One of the conversations that we had the last time we met in March was talking about how people wanted to sort of think about how they would assess what students are learning in their courses where they're teaching computing. And the discussion that we had was, well, maybe what we should try to do is identify what the goals we have are, so that we can evaluate them. And so when you jumped in, Sean was talking a little bit about sort of the difference between continuous problems and discrete problems, and kind of what he wanted students to get out of doing the discrete problems. So we're just kind of sharing broadly right now about what are the goals we have for students when they do computing.
I'm listening.
Okay.
So I can go next if we're waiting, or if someone else's turn. So I think that I have very different goals for computation in my intro level classes than with my upper level undergraduate classes. And at the intro level, it is, I try to make it I try to make computation a tool for them to visualize something more easily, just as a tool to understand the physics better. And, along the way, I hope that they enjoy doing something with Python and they learn something, but that's not my goal for them. And then in the upper level classes, my goals are more in line with what you had in the document that you showed us, where if you're given a problem, you should be able to solve it on a computer, especially when you get to problems that you cannot solve analytically or could be make your life much easier to solve using computation.
Cool. Hi, Josh. Oh, you're muted.
Sorry, I'm late.
No worries, no worries. Sorry you got shifted by a week.
Okay.
I won't make more excuses than I already did. So maybe you introduce yourself briefly, because I'm not sure that Steve has met you or knows who you are. So Steve is just joining us for the first time this month.
Oh, sure. Yeah, I'm Josh Samani. I'm a lecturer at UCLA in the physics department, and a passionate pick-upper.
All right. So just to briefly catch you up, Josh, there's a document if you look at the chat window, there's a link to a document where I'm keeping some notes. We're just kind of going around and chatting about sort of overarching goals that we have for teaching computation, and if those are different between, say, an intro course and an advanced course, and if so, how they're different.
Got it.
Tony, you want to take a turn?
Yeah, I'm still I got a new computer, so I'm messing around with it. But anyway, one of the things I was a little late in getting to that document, but I finally did get it. And one of the things that I'm not still very good at doing, because this idea of learning goals, I began thinking about it seriously during the fall development workshop. And so you think about it and you think you're going to implement it, and you look at your students and you're not so sure that they're getting the same learning goals that you have. And so one of the things I would like them to understand is algorithmic thinking, which, I keep talking about it like, you have to when you're thinking about, right now we're doing E&M, and then you're going to cut these charges into small pieces and add them together. You know, we've done that for a whole bunch of problems, but it seems like you always have to tell the students, hey, we just did this the other time, so we're doing the same thing. But that's one of the things that I would like my students to learn how to do, to think algorithmically. So that I can I echo what you've written there. But I'm really fascinated with the stuff that says how things can go wrong, because that's what my students would benefit from in troubleshooting, you know. So.
Can you say a little more, Tony, about what you mean by troubleshooting? What kind of situations do they get into? What do you want them to troubleshoot?
Of course, the easiest troubleshooting is to use a print statement. But there are some things that it seems like my students are they're getting into the same problems over and over again. Well, we need a loop. Now, they know that a loop has to be there, but it's not quite clear that what we're doing when we have a delta T. That's one of the things that is a problem. Why do we need that delta T? And even though so I've also done something lately where I have them do a problem by hand, and then they're going to do it computationally. And surprisingly, they're very good at doing it by hand, but then when it translates to computational, then they're like, oh, I don't know how I can do that one, which makes me feel like the algorithms are not lined up with what they're doing in problem solving itself. They're more comfortable solving the problems than they are with using an algorithm to solve that problem. That's what I meant.
So you mean they can follow the steps themselves, but they can't translate it into a computer code? Or
yeah,
something
that's for sure. Yeah,
different?
yeah.
Yeah, so Steve, that's a really good point. So when you Tony, when you say they can follow the steps, you mean they can, like, I mean, essentially that the doing it analytically like that is doing it algorithmically, right? It's sort of, where do you see them struggling with the translation to code?
Oh, okay. I need to think a little bit about that. Because I mean, one of the recent examples that I can think about was we were just basically trying to look at a moving proton, and so it's the Biot-Savart law they're using to calculate the magnetic field, you know, and so they really do need the formula for the magnetic field. And VPython does it really well. You can do vectors really well, cross product pretty well. But so what was the problem was basically, so you have all this stuff. I think I haven't done a very good job of telling them what's more important versus what's least important. So they get hung up with, okay, now I have my force and I have my force or my magnetic field, but then how can I show it visually, and how can I iterate that magnetic field so that it kind of so I'm calculating the magnetic field at different points in space. So that means they got the formula right, but they didn't get the fact that well, if you're going to move this thing, you really need to use the momentum update equation, which we've talked about a lot. So that's a little tough, because we spent a lot of time talking about the momentum update, and that's where the hang-up comes in. So part of the problem is me, I think, because I haven't been very clear about the fact that this thing is going to be used over and over again. And so once you're done with that, you're not going to use it again. So it really doesn't seem to be a big problem. It's more like, I guess we did that the other day, and maybe I'm hand-holding them too much also, because they can come to me and say, well, how do we do this thing? So it's just that's a problem, and I may have to look carefully to identify where the problem is. But they seem to calculate everything perfectly until they got the B field, and then now it was just about moving this thing. That was where the hang-up came in, moving the proton, and calculating those B field points was a hard thing for them. So maybe I'll think about it as we go along.
Do you think they were so tired after they figured out what the B field was as a function of space that they didn't have the mental energy left to think about the dynamics?
No, I don't think so. Mm-hmm. Because they had already done, I mean, this is, so second semester, they already did the momentum update equation in last semester, and they've done a couple of those. So it almost is like, I mean, and I'm saying this, there are a couple of students, maybe 3 students who can do that pretty well. But the rest of the guys were having trouble doing that. And so I had to do some hand holding until they were finished with that. So I can't quite tell. And these are good students, engineering students who seem to know what they're doing. If they're able to calculate that, you would imagine that this is a small step to just getting everything done. But yeah, that's all I have.
Thanks, Tony. Yeah, I mean, there's a lot in there too in terms of thinking about what's more or less important, right? When you're thinking about what you want to do in your class, and also the other thing I heard a lot was thinking about the messaging that you're doing in the classroom, right? When in an intro course, you're often using the same algorithms over and over again, and so how do we message to students that that's the case, right? How does that show up both in your lecturing and also in your activities? Great stuff. Ernie just joined us. Ernie, I don't know if you know Steve, but maybe introduce yourself if you don't mind.
Yeah, I'm Ernie Behringer from Eastern Michigan University. Also involved with developing the AAPT computational physics recommendations. Sorry, I'm joining late, but I'm just listening tonight, I think, pretty much. I haven't had a chance to look at the learning goals.
Cool, no worries. So Steve, I don't know if you how you feel about sharing, but I mean, kind of thinking about someone who's been teaching computation for a really long time. Thinking about what your goals are when you teach it, and maybe letting us know, giving us some of that wisdom.
Okay, I'm big on sharing, and I'm so big on sharing that what I did to remind myself was look on the web for my course syllabus. So I have course goals. Whether or not I actually achieve those goals is another issue, but here's the stated goals. 1, to be able to use a computer to solve a variety of problems that arise in solving or modeling problems in the physical sciences. 2, to understand how simulations of physical systems can result in new insights and better physical understanding. 3, to be able to judge the effort involved in differing approaches to problems and to be able to select the most appropriate one. 4, to gain familiarity with error analysis and numerical approaches to physical problems. 5, to be able to quickly produce publication quality graphs. 6, to be able to write structured, readable computer code. 7, to develop computer skills that will be useful for classwork and research. 8, to have fun. That's it.
Would you mind repeating the second goal that you read?
Not at all. to understand how simulations of physical systems can result in new insights and a better physical understanding.
I was trying to type as quickly as I possibly could. Those
you could
different.
just get it on the web.
Oh yeah, do you have the Google Doc open, Steve? Can you paste the link for us just in these notes?
I don't know if I could do that from my iPad. I could probably
Fair enough.
type it open.
Maybe you can tell me what to Google and I can paste it in.
Yeah, physics.indiana.edu
Okay.
/SG.
Indiana.edu/SG.
Yeah. /P609.html.
P609.html.
Yeah, that'll take you to the main course page, and then there's a link to the syllabus.
All right, got it. All right, I'm gonna drop it in here for folks. Cool, thanks.
My pleasure.
Yeah. So Steve, have you ever taught, just by way of background, have you ever taught introductory physics courses with computation, or has your experience been mostly with physics majors?
Exclusively computation and physics majors, really, or, well, more advanced students from other sciences, but never, 201, whatever you call it, 221, 208. Not introductory mechanics. I never introduced computation to that, and I've only taught that course rarely.
Mm-hmm.
I think I was forbidden for teaching it again after one of my colleagues gave a wrong explanation for the solution of a quiz problem, and I gave the same quiz problem again the next week, and they still couldn't solve it.
Fair enough. Fair enough. Josh, you want to tell us a little bit about your goals for teaching computing? You're on mute.
Sure, and just so I'm clear, is this for exclusively introductory courses or just generally speaking?
So the way we're talking about it, depending on the experience, so thinking about, intro and advanced courses, if they're different, sort of distinguishing between the two, if they're not, talking about the overlap, so forth.
Okay. So my experience is with both. I'm teaching a computational physics course next quarter at UCLA, and I introduced some computation into the introductory mechanics class last quarter. And increasingly, my learning goals for computation and learning goals for teaching in general, physics in general, have started to merge in the sense that I've started to feel that the things that my students can benefit the most from in my classes are certain things that working physicists are very good at, but that students tend not to be, like, for example, scaling arguments or order of magnitude estimation, dimensional analysis, all of which I think fall under the category of having these sophisticated cognitive frameworks that these introductory students or even physics majors seem not to really have and only develop much later, maybe in their careers as physicists, or maybe never. And so I'm really, the reason I asked about your second learning goal was that it sounded similar to my general goal, which is how do you gain physical insight in some sense from using computation? And in my mind, gaining insight has a lot to do with these sort of heuristic things, or maybe not even heuristic things, but these things like scaling behaviors and just trying to understand a system in some simple, powerful way, as opposed to super complicated analysis. So my learning goals for computation, I think, are very much going to be centered on the idea of how can you be confident that you know what a system is doing, and in what ways can computation augment the tools you may already have for understanding physical systems, like dimensional analysis or scaling laws or things like that. So I'm starting to design a lot of projects where students are explicitly asked to evaluate their reasoning, evaluate why or how they're confident that a certain method is working the way they think it should be working, evaluate how a computational model can either confirm or, maybe change their intuition about a particular system, things like that, I would say. So this sort of, I guess you could call it metacognitive stuff, like, evaluating their reasoning by using computation as yet another tool in their toolbox for gaining insight and confidence building.
Do your students check conservation of energy when they're working in a system that should conserve energy?
Well, I don't know if they would do it on their own, but the projects certainly ask about all sorts of conservation laws, conservation of energy, angular momentum. Even there's something I've been learning about that I thought was very interesting that I'm going to introduce into one of my projects called backward error analysis for numerical solution, ODE solving schemes, which basically has to do with finding a quantity that's exactly conserved by a numerical method. And it's really interesting. It's very much along those lines, and explains why, for example, certain integrators are so good at predicting long time behaviors of chaotic systems and stuff like that. So that's totally the kind of thing I'm interested in, getting students to check things like energy conservation or check certain limiting cases or special cases, things like that.
Cool, thanks, Josh. We had somebody join us, but I think it's forehead.
Override protocol has been initiated.
Hello?
I think it's Rob.
Yes, hi. Sorry I'm late.
Oh, there you are. Hey, Rob, how are you?
I got it, and then the link didn't work right, so.
No worries.
All right, so continue. I'm really just here to eavesdrop on this conversation because it affects me, but not directly.
Fair enough. Yeah, so just catch up really quickly. So we've been going around just chatting a little bit about the learning goals that people have sort of generally for teaching computation in both intro and advanced courses. And there's in the chat window, I don't know if you have access to it, Rob, there's a Google Doc where I've been taking notes on the conversation that people have had, with these what I would say is a wide variety of different kinds of goals. So just for you to have a gander at. Yeah. So, I think one of the things I would be curious about, right? So we've talked about sort of broadly speaking, what kinds of things folks are interested in having their students develop an understanding of broadly, right? But when you're thinking about your specific courses, are there specific things that you're interested in? I think Josh kind of started this, and so maybe we'll go back to him a little bit, about specific aspects of a course, right? Where sort of there's a natural connection there to something. So either in a computational physics course or in your advanced physics course or your intro course, that you're really trying to draw out the understanding of a particular intersection, perhaps between a concept and an algorithm, or a way of thinking and a concept, or something like that. I'm curious how people are thinking about those kinds of things.
Can you say that again? I got confused.
Sure. Yeah. So the goals that are articulated up here are sort of general goals, right? So algorithmic thinking, right? Or this idea of gaining physical insight. But when you go into a course, a specific course, let's say quantum mechanics, right? how does that manifest itself in that course, right? So what are the specific things that you're looking for where you're looking at the intersection between, you know, the specific algorithms that are appropriate for that course and the concept, or the ways of thinking that you're trying to emphasize and the algorithm, or the ways of thinking and the concepts?
Suppose you said you wanted a student to be able to solve Schrodinger's equation.
Right. Yeah, I guess my question is given that you want a student, just like, how do you want them to solve it? What meaning do you want them to make out of it? And why would you do it with a computer? Like, what meaning are you hoping that they make out of it that is different, let's say, from, you know, just solving the eigenvalue problem?
You mean analytically?
I have a, oh, sorry, go ahead, Stephen.
They might be able to solve a wider variety of problems.
In addition, I would say that they can look at sequences of numerical solutions that they can do rapidly that they won't do analytically, and they can gain some insight there about how rapidly, say, the tails grow on a wave function depending how close you get to the top of a well or something like that. So that's a kind of insight one might gain numerically that might be more difficult to do, or really hard to do analytically. One thing that Josh mentioned earlier, which is something that I think is very important, is thinking in terms of scales. And the scales actually allow you to determine what's important in a problem. And so I think that's something that you can explore a little more easily. Now, you definitely have to write the equations and identify the scales that way. However, the exploration of how rapidly things change as you change relative values is something you can do quickly once you have the model, but maybe a little more difficult to do generally, analytically. So that would be an example of something that computation really is good for.
Yeah, I think that's a fantastic one. Oh, sorry, Josh. I was saying that I think that's a fantastic one because it's sort of blending this idea of ways of thinking, right? Thinking about scales with the tool, right? The tool facilitates a better, or maybe an easier way of being able to explore scales. So that's kind of the thing I was sort of suggesting, and Ernie obviously much better at articulating it.
So I think when I was a student, I'd do a lot of algebra, some calculus, and get an analytic answer. And I'd be too tired to actually think about what it meant. I mean, you wouldn't graph it. You just say, okay, all the terms are there, and you know, it's done.
I just wanted to add to what Ernie said. Say, for example, in a planetary motion problem, which I think is something that a lot of us probably use for introducing students to a problem where they can use a numerical ODE solver, for example. You could ask a student on an exam on pencil and paper, what happens when you rescale the radius, the initial velocity, and I don't know, Newton's constant or something. And a student can find out that, to determine that answer by plugging in some rescalings. But like Stephen said, I think very few students would really appreciate what that actually means, and like when you watch the system evolve over time. But as Ernie said, you can change all of those things in your simulation and see it happen. And I think that's so much more convincing than just writing down the answer to the rescalings on a piece of paper. At least in my experience, like when I ask students to do a scaling argument and they get an answer, I never really quite feel like they understand what it meant because they don't see it happen. But.
I'm sorry I came in late, but I'm wondering, did people articulate differences between intro and upper level?
Yeah, I think so. The if you do look at the document here, the Google Doc, I think Michelle did a really nice job of explaining her goals, that are the way that they're different for intro and advanced. So she talked about how in an intro course you might be more interested in helping students visualize things, helping them to sort of like realize that it's a tool that can do lots of stuff, and that that they get some enjoyment out of it. Whereas in an upper level course, it sounded like her goals were much more focused on, if I give you a problem, you should be able to solve it.
Okay.
Right? I think that was a really clear distinction that I heard. Yeah.
Okay. I saw that, and I think that's a good distinction. So in some sense, with the intro course, I guess I'm thinking mechanics mostly. It's sort of like the Euler Cromer and ride that pony as far as you can. And then for maybe the intro and E&M, getting used to slicing and dicing charge distributions and adding things up. I'm curious if there's more.
Well, circuit problems, system of equations, you can do pretty automatically with Gaussian elimination.
Okay. Mm-hmm. Yeah.
What I've really wanted to do, but I don't know if this might already be out there, but thin lenses, like simulate a thin lens and see the rays bend and see the image form, and not a simulation that programs in the answer the way you see it in a textbook, but a simulation that starts from Snell's law and where the rays actually bend according to Snell's law and seeing what happens.
Yeah, I think it would be great to have something like some glow scripts to do this, right? That's freely available. But I guess you're also thinking that this is something that they do. If you have a lot of surfaces, it gets a little bit tedious, I guess.
I think both would be interesting, but yeah, I mean, if either were available, it'd be good.
Yeah, I agree.
I actually have a student who proposed something very similar to that for their computational final project. And their first code submission's due next Friday. So I'll let you know if something comes out of that.
Oh, that would be great.
Yeah, we should just crowdsource students to do all this for us and computation.
It's actually not a bad idea in a way to sort of develop a whole tool set. But, yeah.
So one of the things I remember, Ernie, from the APT document was that, coupled to sort of these computational learning outcomes, right? Thinking about algorithms and thinking about the ways that students understand it, was also sort of more like broader sort of scientific technical skills.
Yeah. So there were.
Go ahead. I'll let you.
So my head hasn't been totally there with the document, but yeah, there's a distinction between computational physics skills, which involve gaining physical insight, choosing scales, things like that, where you really are trying to gain knowledge, versus technical skills, which are really the machinery of generating I guess deliverables in some sense, right? The technical skills are all about, how do you generate a graph? Can you generate graphs? Okay, that's not exactly completely decoupled from physics, but in a way you can think of it as, it's a mechanical thing to do. Then you can ask questions like, well, once you know how to do that technical stuff, like choosing an algorithm, making visual representations. Then you can ask questions like, is it the best algorithm? Is it the best way to represent data? Is it actually communicating the physical point that I want to communicate? Those are sort of higher level skills beyond the machinery of, I can make a plot, right? So there is a distinction between the machinery versus extracting physical insight in the document. It's not super well defined because I think we need people like Danny to really get at the borderline. It's going to be a fuzzy border, I think, but how do we distinguish between machinery versus what it means to make sense in physics, I guess?
Do you tell students how to make a plot? Or do you just say, any way you can make a plot is fine with me if you can do it to a certain level?
I think it depends on the course. If it's an intro course, I will give them scaffolding, templates of this is a code that's minimally working that you can make a plot with, and all you have to do is change the function pretty much. And even then, they'll still get confused and think they have to totally rewrite things. And you really have to be very explicit with introductory students, I find. Maybe my cohort is different than your cohort, but that's what I find. So with upper level students, it's more likely they've been with one of either my colleagues and I who have already required them to do things, and I'll be more likely to say, do it how you can do it.
I'm curious, do other people have technical skills that they're trying to get across to their students maybe in their advanced courses?
I do. Well, in my computational physics class, which I think is a good place for it, I have very specific, I guess, learning goals for the students in terms of technical programming skills. So I want them to know the appropriate terminology. So if they're they're learning a marketable skill by learning Python. So I want them to come out knowing good programming style, knowing how to write efficient code and know the correct terminology like scope and things like this that you would hear if you decide, like, not all physics majors become physicists, of course. Most of them do not. So if they end up in a computational field, that they could kind of hold their own there based off the fundamentals that they learn in that class specifically. But I don't do it in any of the other classes.
Is that senior level, sophomore level?
It is technically sophomore level. We have freshmen, sophomores, juniors, and seniors in there. It's my first year teaching it, so that may be why, like, some people might have waited because it used to be taught in EJS. We have freshmen because they want a double major in CS and and physics. So yeah, it's technically sophomore level or junior level, sophomore level.
What about things like using GitHub or an IDE?
So in my upper level E&M course now, we do use GitHub or Git repositories for all of our work. So they have no exams, but they have 2 projects. So this is a standard like electrodynamics course, but it has computing in it. And so the projects that they turn in involve them submitting their work in a repository. I give them feedback in that repository. They, pull down their feedback. They make changes, and we've been doing that. The first project, it was an individual project, so they each had their own repositories. The next project that they're working on is a pair project, so they have a repository for the team, and we're going to do the same process. So we're trying to bake a little bit of that in. It's for our students, this is the last course they take. This is their second semester senior level course. So, you know, I don't know if you all had a chance to look at the document that we're generating here. It has it, you know, this idea of version control is one of the big learning goals that we have. And so hopefully that'll get baked in much earlier. But it's something that I'm definitely doing in this upper level course.
Sorry if I missed it, but did you say that they're using GitHub just for the projects or for homeworks along the way as well?
So we use it for, so they still turn in pencil and paper homework, but there are homework problems that they have that have some computing, and they turn those in individual repositories. So each homework problem has, each homework problem that has that is computational has a repository, because I'm using GitHub Classroom. But the projects are also turned in through GitHub Classroom, but then they're recurrent in the sense that they continue to use the same repository. And if you haven't had a chance to check out GitHub Classroom and you're thinking about what to do in the fall, totally check it out. It's free. They send you a bunch of free crap to give your students, which is kind of cool.
What about if I'm planning on using it in 2 weeks?
They will set you up in about 3 or 4 days. Like, they can do it really, really quickly. Essentially, you make a request to them. They just kind of check your website, I think, and then they just take your GitHub account and give it some new permissions.
So I tried to set mine up in like 3 days to use this semester. And I will say that how I had structured my class and assignments in terms of repositories was not correct for how you would do it with GitHub Classroom. So I thought I was going to do it, and then I abandoned it like the day before because I didn't give myself enough time to understand how my repository structure should be.
Yeah, I would say, Josh, if you're thinking about doing it, watch some of the videos, because like there's some really simple things that you can do to make it easy on yourself, that I didn't learn until probably the 3rd week that I was using it. So you can create a repository that has stuff in it that you can populate the repository for students, which is really helpful when you're giving them feedback in the repositories, because then you don't have to copy and paste everything in the initial repository they pull down. Has all of your, instructions and a feedback document. And there's also some scripts online that I can point y'all to do a very, very quick, pushing of the repository for students, because each student has their own, in principle, can have their own repository. So you can end up with as many repositories as you have students. So if you're pushing all that stuff up, it's kind of annoying, but there's scripts that are that somebody has made available to make it very easy for you to do that.
Can the students see each other's repositories?
They can if you want them to. So you can deny access, and you can also grant them access to do that.
So Classroom gives you free private repositories for all of your students if you want them, which is what's really great, because that's not typically a free feature of GitHub, if I remember.
All right. Well, I'm sensitive to time. I know it's for those of us on the East Coast anyway. I'm not on the East Coast. I'm on the 3rd coast, which is the best coast. But it's still Eastern time. But I want to thank y'all for joining us again this month. It's a great conversation. I think a lot of really great stuff is coming out of this. I will try again to sort of spend a little bit of time distilling down all of our raw notes here into something that we can look at together and sort of just keep track of everything we've been talking about. And as far as learning goals go, I'm happy to keep sharing, the stuff we're doing locally. It pertains to us locally at state, but if that's helpful for people as they're sort of thinking about broadening their efforts and so forth, I'm happy to help that.
Yes, please.
Okay.
Yep.
Condolences on the loss, by the way.
Condolences. What did we lose? Did we lose something?
Weren't you guys in the tournament and lost to someone?
Was it hockey, basketball, the other sports ball?
Basketball.
Wait, there's sports puck and there's sports ball. I know there's a difference between the two. So, anyway.
He lost them all.
Sean is pissed right now. All right. Well, so I think we have another meeting. Let me just make sure. Let me just check the calendar really quickly so people have a sense. I believe we have one scheduled in April. It is actually 2 weeks from now. So April the 4th. I think we'll probably have a little bit of an internal conversation around how things went today and what we think to have as a topic for that April meeting. But if you have particular things you're interested in, that would be great. We could also, one thing we could always do is we could do a roundtable share of what people have been doing this semester, which is always nice because you have to see some specific things. So if folks are interested in that, we can just be in touch on Slack and see what people think. Cool.
And as one last thing, I was wondering if we could, if this list of learning objectives would be a good thing to share publicly on the PICUP site. So if either people have syllabi they want to share, just lists they can go somewhere on the PICUP public site. Yeah.
So if people have just another 2 or 3 minutes, I'll just give you a little update on some of the stuff that we are working on our end anyway. So one thing that we really want to do is we want to start highlighting individuals that are doing stuff. So Marie and I are working on essentially a questionnaire that we would give to people to fill out. And then those questions would be like, a little bit of demographic information, a little bit of sort of your personal goals for teaching computing, a little bit about the ways that you do it and the constraints you have at your institution, giving people some user stories, if you will. And that thing we think are both going to be highlighted on the website, but also, I don't know, I'm assuming most of y'all received like the new sort of MailChimp email. So, the sort of like more graphical, I don't know, it's not just plain text like it has been lately. We are hoping to highlight somebody once a month in the same way that sort of AAPT does, right? So, putting those user stories up and then sort of sharing them out through this MailChimp to the broader PICUP community. Because right now we actually have about 250 people that are signed up for the PICUP community, even, that are getting sort of the contacts every couple weeks, and we have a sort of an open rate of about 30%. So, you're talking about 80 people or so that are reading these things. Michelle, sorry. Yeah.
I don't think I'm on this email list. How do I sign up for that?
I can double check to make sure that you're on it. Basically all I did was I took the Google mailing list that we have and dumped it into MailChimp.
Okay. You may need my Davidson email address.
That might be it.
I was
all right.
straddling jobs when I was at the PICUP workshop.
Okay. Yeah. Let me see if I can look for it in a little bit and see what I have.
I can send you an email.
I have a Gmail account for you on this mailing list.
Okay.
So yeah, just send me a note and I'll make sure to update it for you.
Okay. Thanks.
Okay. All right. Well, thank you all very much again. I know evenings are difficult for folks, so I appreciate you spending the time with us.
Thanks, Danny.
Thanks.
Right.
Thank you.
Yeah.
Bye.
Bye.